All right, we're starting a whole new section. This is the section where we take everything from Bio 101 and everything from Bio 102 and we put it all together. It's population ecology, distribution of organisms. So this is really, if you remember 7th grade life science, way back in the day for some of you. For others of you, it seems like yesterday. You talked about habitats, and you talked about where organisms live, and these biomes and things like that. That's what we're getting into today. A little bit more depth, and by a little bit more, I mean a lot more depth than you did in 7th grade. But it's still basically the same concept. Things live out there, and they got to live somewhere. Now, there are 2 big biomes that organisms live in. Just, if we're going to separate things out at the large scale. Terrestrial and aquatic. What does it mean to be terrestrial? On land. And aquatic? In the water. So if I was to ask you, what's the difference between terrestrial and aquatic habitats? It's like you know this before we even start. These terrestrial habitats are the ones found on dry land. You can't find much of that these days in Virginia, apparently. I went out in my backyard and I sank. I actually lost a shoe. It was one of those days. Fun life story for me, and this will date the video too. I just put 8 fig trees in the ground at my house. I was very excited because I love fig trees. Figs are like my favorite fruit, and I will eat them like crazy. People have warned me about figs. They're like, they're going to produce too many fruits. That's never been an issue. So I was planting these fig trees in this, what I assume to be terrestrial environment, because there were trees. And I was like, trees, terrestrial. There's mud, I see it. Unfortunately, perhaps you experience this at your house too. What looks like solid mud apparently has, solid dirt is just straight up suctionable mud. You put your foot down and you sink quick. Anybody else have that going on at their house, or is it just me and, okay, good. It's me and my bad drainage problem. But by God, I got those fig trees in the ground, and I'm going to hopefully allow them to suck up all this water, because this is how it works in my head, and really dry out the land. So I'm working on turning my apparently pseudo-aquatic habitat in the backyard back into a terrestrial habitat. Now, these terrestrial habitats are impacted by sunlight. Kind of important. You'll notice that some regions of the Earth get more sunlight than other parts of the Earth. That's based on latitudinal variation. Now, if you remember, latitude lines lay. Right? They're the horizontal lines. So, based on where your latitude is, you're going to get more or less sunlight. Typically, around the center of the Earth, the equator, you're going to have much more sunlight, much more direct light. Now, because of all of these different latitudinal coordinates, based on differing amounts of sunlight, you get air circulation. You've experienced wind, right? Wind blows. There are definite, predictable patterns to the wind. We used to use these back when we were sailing ships, sailing schooners and things from one continent to the next. As the sun warms up the air, it gets hotter and hot air rises. We good on that idea? So the air that warms up goes higher. It's also why in the winter you've got a fan setting. If you can switch to your fans in your house, you've got one setting that blows air downward, and you got one setting that blows air upward, that sucks air up. Did you guys not know that? Check out your fans at home, the ceiling fans. There are 2 settings on it. One for up and one for down. So one will blow air downward. You can flip it in the season. I know! Life hack, right? And then in the other seasons, you flip it and it will suck air up. Why? Because in the summer, you don't want to actually blow... Yes? The vast majority. If the fan has been built in the last, 15, 20 years, yes. Check it out. There's a little switch on the side. No. What? Make sure it's off. Oh, thanks. Sorry. Don't stick your hand up in the fan when it's on. I forgot. You guys need those lessons. Oh, Crow's not here today, so, you guys will be fine. So, check out your fans, because what will happen is, in the winter, You want to take that warm air that's rising and blow it back down. In the summer, you want to take the warm air from the bottom and suck it up. You still do get a little breeze. The difference is which way you're blowing the warm air. So warm, wet air rises at the equator. As it rises, it cools down. And when it cools down, that warm, gaseous water vapor condenses into rain. So the air is going up. At a high altitude, it begins to cool down. And then when you get about 30 degrees north or south of the equator, the air drops suddenly. So you've got warm air rising, cooling down, condensing, water falls. Where that water falls right around the equator, what are you getting? What grows there? Rainforests and stuff, right? That's why you got all this rain, and that's why they call it a rainforest, because it's always raining. Then the air's lost its water, and it's cooled back down. It's down on the ground. You don't have much rain at about that 30-degree latitude point. So if you don't have much humidity there, at about 30 degrees north and south of the equator, what are you getting in that region? Not much rain. Deserts. Okay? So there you've got up Mexico, Texas. That's about 30 degrees latitude. And then I think around the Sahara? I forget what the other desert is lower down. Atacama Desert? Oh, well. I don't know my world geography. All right, so you've cooled that air down. It drops. It's got no water. The air starts to heat back up. About 60 degrees latitude, it's warm and wet again. So it starts to rise, and that leads to more precipitation. We get closer to the poles, and the air cools down. Where it cools down, you end up with even more dry areas, and then there's one more warm up and drop. Do you know in Alaska is the largest continental rainforest? You don't think of rainforest in Alaska, but it's rain-like pretty much every day, because that's where all of this air is rising and condensing suddenly. Now, the air movement caused by hot air rising. Whenever hot air rises, other air has to come in and fill that space. So air is going up, other masses of air fill in the space, and as that air moves in to fill the space, that causes wind. So these winds end up being pushed to the east and the west based on the revolution of the Earth. There are a bunch of other influences on climate, though. You got seasons, bodies of water, mountains. All of these are abiotic factors. What does it mean to be abiotic? Without life. So seasons, bodies of water, mountains, doesn't depend on life. It just happens. We've got different levels of sunlight striking the Earth at different latitudes. The deal is, though, the Earth is tilted. And because it's tilted and spinning on that axis, sort of wobbling around, what you end up with is seasons. As the one part of the Earth is facing closer to the sun, getting more light, that's going to be in summer. And as part is tilted away, that's going to be winter. That changes, ultimately, the temperatures and day length. It feels like it gets late at 5 p.m. now, doesn't it? It's dark outside. But for somebody taking this class in spring or in summer, it's going to be just the opposite. It's going to be light out until 10 o'clock. But it's not just the tilt of the Earth that plays a big role. It's also the proximity to bodies of water. Okay, Bio 101 idea. Do you guys remember about the properties of water? Did you learn about those? And why water is so important? What is it about water that allows it to very slowly warm up and very slowly cool down? What? The specific heat. Water has a really, really high specific heat. In comparison, metals have very low specific heat. Tinfoil, very, very low specific heat. So what will happen is tinfoil or metals heat up very fast and they cool down very fast. If you've ever tried to boil water, and I assume you had, you'll notice that the pan heats up a lot faster than the water in the pan does, right? I mean, that's kind of just the way it is. You don't touch the pan with your hands, but you can stick your hand in the water for a while. Don't do it forever. That will allow, so the water heats up very, very slowly. If anybody gone swimming in a lake before? What season do you typically go swimming in a lake? Summer. You don't go in early summer or late spring when the temperature's hot on the outside, because the temperature in the lake is still really freaking cold. But you can continue to go swimming in a lake out into fall after the temperature outside has dropped below when you'd want to swim, because the water in the lake is still warm. Humid regions that have a lot of water in the air, tend to have a more stable temperature. It rained yesterday. Last night and this morning, it's about the same temperature, regardless of what sun's out there warming it up. You may have noticed that when it's raining or precipitating, when there's a lot of humidity in the air temperature between night and day stays fairly constant. But when there's no very, very low humidity, which, welcome to Virginia, we're not going to experience that very often. But when there's low humidity, the temperature changes are dramatic. If you were to go to a desert, what are the temperatures like during the day in the desert? Really hot. And how about at night? Really, really freaking cold. Nobody really thinks about the desert being cold, but it is. Because there's no water there to retain the heat in the atmosphere. Yes? Are rivers always the same temperature? Like, no. Especially along the length of the river. In the same spot? From day to day? It depends on the depth of the river, truthfully. Because if it's a shallow river, that's wide, and depending on what substrate it has, what rocks are under it, it will absorb a lot of heat and warm up. Definitely, seasonally, rivers aren't the same temperature, because sometimes they freeze and sometimes they're running. So I'd say probably not so much unless it's a very large river. The Mississippi might, because it's really deep and really wide. But the James, I mean, that will change. That'll fluctuate in temperature daily. What you'll notice, and we talked about this when we talked about paleobiological organisms, is by bodies of water, by the ocean, you get temperate regions and you get a lot of organisms thriving. As you move inland, away from bodies of water, you get more and more desert conditions. And they got mountains. Mountains are like ramps for air. And that's apparently how I'm viewing them from here on out. They force warm, wet air to rise. So as an air mass that's warm and wet hits a mountain, it's going to start rising up. What happens when it rises up? So warm, wet air hits a mountain, starts to go up. It gets cooler and it condenses and it drops that water. Right. So it drops the water on this side of the mountain. So what happens on the other side of the mountain? You don't get much rain. You guys have seen this happen all the time. You've watched snowstorms like a hawk because you're students and you're like, I want to get out of school. There's a snowstorm coming. It's heading toward the Appalachians. And what inevitably happens? It hits the mountains. And what does it do on the mountains? It drops all the snow. And then it hits us and it's like, oh, look, a cloud. In Danville, where I was, it was a lot worse. We never got snow. We barely got, well, we got a decent amount of rain, especially recently. But what happened was the Appalachian Mountains would always stop the whatever front was coming our way from the Gulf of Mexico.
But at least they have the tank museum.
Not any, it's sort of dying.
Well, like, there was that time when they were going to move all the tanks.
That's true.
But then they didn't want them.
They do have the tank museum, and they do have twice a year in Danville, in case you guys want to go, a interactive flamethrower demonstration. It's worth the trip just for that.
Danville. Barnes & Noble closed down.
All right, but that's enough about the land. let's talk about the aquatic biomes. All of those things in the ocean. They're characterized by, these ocean environments aren't characterized as much by temperature as much as they're characterized by their physical and chemical properties. It's all about light. In the aquatic ecosystems, you have light absorbed by the water. You probably noticed this. As you go swimming, the deeper you get, the darker it gets. It gets a little bit harder to see. You also get a lot more pressure the farther down you go. Light gets absorbed by water as it goes down. The longest wavelengths are the ones that are absorbed first. So the red light disappears early on, and then the yellow light, and then green light, and blue continues down for quite a ways until it too disappears. Now, why would light be important for an aquatic ecosystem? Come on, guys, you know this. Yeah, just like on land, you have photosynthetic organisms forming that sort of base level, the bottom of the food chain. You need these organisms to be able to take in light and convert it into what substance? Thanks for being awake, guys. You learned a lot about it last semester. So photosynthesis. Yeah, thanks. Photosynthesis. You have light coming in. It's striking these photosynthetic organisms. They begin to produce a complex biological molecule known as what? No. What? Glucose, yes. Says the guy who remembers cellular respiration. Well done. So, they're producing glucose. Other organisms are going to take that glucose and incorporate it into their bodies. Break it down, get some energy, use those parts. The deeper down you go, the less photosynthetic organisms you have. Ooh, and that leads to some really cool stuff. Vertical migration. Have you ever heard of vertical migration? Okay, here's how vertical migration works. I probably shouldn't be talking about it at this point, but it's really cool. So, photosynthetic organisms don't just live at the top of the surface all the time. They're going to move based on the amount of sunlight present. So, sometimes they hang out a little bit lower down, and then as light decreases, they migrate upwards. And as they migrate upwards, there's going to be their predators following behind them. And then as the predators follow behind them, the even bigger fish follow behind them. So you get these, during the day, if you tag a fish, you can watch them go up and down in the water column based on the migration of the photosynthetic organisms. It's super cool. It's been recently shown that great white sharks do this. Male great white sharks are going to vertically migrate in the water column from up near the surface down to, 100 meters, really, really deep. They're going to go super deep down and then come right back up all through the Pacific. Kind of neat. So light gets absorbed by the water, and that leads to different zones. The photonic zone is where you get light, because that's where the photons are. This photonic zone will have a lot of photosynthetic organisms. Beyond the photonic zone, you have the benthic zone. This is the area in which light cannot penetrate. This is where even the blue light gets absorbed. The benthic zone is where you get all those super cool fish that look like they have fangs, and they look like they will have a lot of bioluminescence. Pardon? It's where the megalodon lives. No, we've talked this about. No, there is no megalodon anymore. I'm sorry, they're gone. But think about this. Hollywood might think that. But the megalodon, this is super neat. You guys have heard of the megalodon before, right? It's a shark that's roughly, hold on. These are 2 feet, 8, 24. Okay, to put in perspective, probably the largest white shark on record is about the size of this room. Okay? The megalodon would be from that wall to beyond the wall in the other room over there. Really, really large shark. Females were that big. I'm sorry, the males were considerably smaller. That's called sexual dimorphism. Usually females are much bigger. But what they've noticed, or what's notable about the megalodon is that early humans came on the scene at the same time the megalodon was in the was swimming around the Pacific, which means that our ancestors, if they went swimming really, really far out because they were dumb, they could have encountered one, and that's really cool to me. Now, the upper layer of aquatic environments are usually uniformly warm, and they fluctuate. Meanwhile, the deeper layers are uniformly cold. So you've got a warm temperature region and a cold temperature region. And where they meet, this sort of space in between where there's a very rapid change in temperatures, that's called a thermocline. Again, you've been swimming in a lake before. Do you ever go swimming off a boat in a lake? Yeah? Do you ever jump off the boat? Yeah? Okay. Perhaps you've experienced a thermocline then. You jump in, the top of the lake is nice and warm, but you hit a layer that is utterly freezing when you jump off a boat. It's about 6 feet down, but you hit that and you're like, oh my god, up to the surface. Have you experienced that? Yeah, that's a thermocline. Now, an oceanic thermocline is typically much deeper, but it's the same idea. You're going to have completely different organisms living in one part in the upper layer than in the lower layer. Neat part is, the bottom of the ocean around the world has a fairly uniform temperature. It's roughly 2.5 to 3 degrees Celsius. Because, again, properties of water. Water expands when it freezes. So it's densest at about 4 degrees Celsius. Now that's going to be adjusted for with salinity, but so at about 3 or 4 degrees Celsius, the water just sits on the bottom. So there is very, very little variation. Temperatures in the tropics, about 5 degrees at the bottom. Up in the mid-latitudes, about 5 degrees. And even at the poles, about 5 degrees. The difference comes at the top layer. At the top layer in the summer in the tropics, oh, it's 28 degrees Celsius. It's pretty darn warm. Mid-latitudes, about where we are, about 23 degrees. And at the poles, 6 or 7. So there's a big difference. The organisms that survive in the top layer, the top of the warmer layer, have to adapt to changing climate conditions, while those that live at the bottom don't have to adapt at all. If you look, there's typically going to be worldwide distribution of organisms that live along the bottom of the ocean, because it's pretty much the same habitat everywhere. Hagfish and such. And that's what we're going to get to talking about global distribution. Now, any questions thus far on terrestrial or aquatic habitats? As you can imagine, I am way more excited about aquatic habitats. I think they're super awesome. Terrestrial habitats, I'm like, there are trees, the end. But water's awesome. Questions? All right. Now, we've talked about where they live. Let's talk about the organisms themselves. Where the species are located is based entirely on their ecological factors and evolutionary history, which is a cop-out answer that means everything is different. Organisms all started in one region, across the board. It's not like every, organism just popped up all over the world at the same time. At some point, there was a distribution point, one place where these organisms would expand out from. Then they dispersed. They went outward from it. Dispersal is where individuals or gametes leave that origin region and go somewhere else. Like this dandelion. You guys have blown on dandelions before, right? A lot of people that are like, make a wish and blow on it. That's the biggest fraud we've ever committed on children. Because we're like, make a wish and blow on this weed. And then what happens? The next year, your whole yard's filled with these things.
More wishes.
More wishes. More wishes that won't come true. Yep. So there we go. Yeah, sad. That got dark. The idea is, what you're doing is you're helping these things disperse. Get away from their point of origin. When an organism is stranded all by itself, when a population of organisms are all by themselves, typically they're going to be that population's left alone because of geographic isolation. Geographic isolation means that these organisms cannot disperse for one reason or another. They can't get out there. I mean, here we got a whole bunch of random little lakes. It'd be really hard for a fish to get from here to here. There's a geographic isolating mechanism. Thank you. So when there's no dispersal, you have isolation. But here's the deal. If you're able to take an organism out of that isolated region, bring them into a new area, and they're able to survive and reproduce, the lack of dispersion was definitely the reason it was geographically isolated. It means that it can survive elsewhere. Those organisms that can't survive elsewhere, you pull it out of one place and you drop it in another and it dies, there's something else aside from lack of dispersion in effect. And this is where we get to the idea of invasive species, which you guys might find a lot more interesting. These are species that can breed and compete with existing species. They invade a habitat, and they can have huge ecological consequences. There are a lot of examples, and there are going to be more and more and more examples. The brown tree snake of Guam. These brown tree snakes are not indigenous to the region. Somebody introduced one. I think that this one came in a shipment of some sort of agricultural product. It came, it laid eggs, and it started hunting all of the birds. Now there aren't birds in Guam anymore. The tree snake ate them. Not just one. I mean, it's all his family did too. Stink bugs. Your house has probably been invaded by stink bugs in the winter, right? I assume. I might be no? You never see these things crawling around in your house? Maybe it's just my house. Okay, some of you guys do. Yeah. They're not supposed to be here. But they are. And of course, the Florida anacondas. I'm sorry, not the anacondas. The Florida boa constrictors. I hate those. The pythons in Florida are a menace. So turns out there are a few reasons. You guys have heard of the Everglades, big swamp? In the Everglades, there are a whole bunch of gators. They're typically the top of the food chain predator. After a hurricane, well, there are a few stories behind this, but one major push is not just pets being released. Typically, when invasive species are found, it's because pets were released in the wild. But what ends up happening here is there were hurricanes, and pet stores flooded. And when the pet stores flooded, the animals escaped. So now you have these pythons in the wild. Well, there's a few pythons met up with each other. They mated. Turns out the wetland is a perfect habitat for them. There are lots and lots of prey items there. They can hunt. They can mate. They get bigger and bigger and bigger. It's gotten to the point where they are now outcompeting the alligators. Not just outcompeting them, but actually eating them. These organisms are top of the food chain predators, and they're in a new environment. There are thousands upon thousands of 15 to 20 foot snakes in the Florida Everglades right now. To the point where there are no restrictions on hunting. They encourage it. Not only do they encourage hunting, they will pay a bounty on it. People use them for their meat. They're trying to make a whole industry about it. Eating the meat. Delicacy, yeah. Skinning them to get make reptile skin bags and such. Pardon? How would you shoot it? Shooting it's one way. No, you don't want to knife it. I honestly don't know as far as how to hunt them. Shooting it's typically what people end up doing, I think. No, your shovel won't go through the vertebrae. How does it digest them? Well, the alligator goes in, and then it gets digested. The scale, yeah. Well, but then anything that's undigestible comes back out. Regurgitation. Pardon? How does it pass it?
No, it passes the scale, right? It's not like you can bite into it.
Right, no, it's literally digestive enzymes. Although there have been several encounters where, like, if it eats the alligator wrong, like a claw will stick up and it'll just slice right down the python.
So did it kill them?
Yeah. Yeah. Heck, there are a few examples of, well, here's one eating a whole deer. This is its mouth, by the way. Here's the deer going in. Here's another baby deer up there. There are examples of these pythons actually bursting because they eat too large of a meal. So that's the Florida python. The northern snakehead. Fish are very invasive. If you go boating, there are lots of regulations about before you go from one body of water to another, you need to clean out your ballast. You need to clean off your boat because you don't want to take mussels or some invasive species from one port to another. Inevitably, cruise ships, all these different ships moving from one port to another will take in larvae of fish from one region of the world and drop it off in another region. Before I get into the northern snakehead, we'll talk about the lionfish. Lionfish are a top of the food chain predator. They're the ones that have spines looking on them, sort of like brown and white. They live in Florida now. They didn't used to live in Florida. They're eating everything in the ecosystem because they themselves are poisonous and they are voracious hunters. So, a lot of the sport fish are being eaten up by this organism. So what do we do as humans? We're like, you know what? We got to hunt these things. How do you encourage people to hunt them? 2 ways. 1, you put a bounty on them. 2, you convince people that they're delicious. They're not. But there's a huge campaign going on in Florida right now, in the surrounding region, to make people think that lionfish are a delectable treat that you should pay a premium for, so that more people will go hunting them, so that the population will decline. Yeah?
So what I'm hearing is never Australia or Florida.
Never Australia or Florida.
So are there any other places I should avoid?
Aside from Florida and Australia. The Zambezi River. That one is, I want to say, it's South America. Yeah, Lake Victoria. It leads up to Lake Victoria because there's sharks in it. Yeah. Oh. Yep.
Basically, never leave your house.
Right. Oh, except for the bugs that live in there. There's some nasty stuff in Virginia. So leave your house. Just, I don't know, stand still somewhere.
Hide under the blankets and pretend that, like...
Spiders.
Okay, just go into fetal position and cry.
Yes, there we go. Another invasive species is the northern snakehead. The northern snakehead is an organism that now lives in the Potomac River, eating its way down the Chesapeake. Because I read a whole book on this one. This one's super interesting. The northern snakehead is an Asian fish. It is a top of the food chain predator. You can see its teeth in there. This fish is thought to have medicinal properties. So somebody bought these, and I forget them, they figured out exactly who it was too, which is weird. They bought 2 snakeheads at a fish market. They were on ice, but they were still alive because their family member was sick. So they bought these things to cook them. The family member got better, so they didn't want to just kill the fish. So they took the fish and they released it into like a drainage pond. Now, this drainage pond was in, I want to say it was Waldorf, Maryland, right behind, it was like behind a shopping center. And a dad and his son were fishing out there. And the son caught, I think it was like a 2.5 foot or a 3 foot snakehead. Reeled it in, and the dad's like, I've never seen this. So he sent the picture to the Maryland wildlife people, and they're like, that's a northern snakehead. Where'd you find it? Because we need to get rid of it. So they showed where the pond was. So the wildlife biologist came out and they did a shock test on the pond. So they ran an electric current through the pond, and so all the fish came to the surface. The problem was they expected two fish, but it turned out there were thousands just teeming in there. In fact, There were so many, there were no other fish, no other bugs, nothing else. They ate everything else, and then when they ran out of the other food, they were eating each other. So you had cannibalistic fish devouring each other in this pond. At that point, they were really concerned, because this pond was about 20 feet away from water access to the Potomac River. And the pond was an overflow pond. So when it rained too hard, the water would go from one to the other. Not only that, these fish are air breathers, which means they can come up and take a gulp of air. They don't need to stay underwater to get it. So low oxygen conditions in the pond don't matter to it. That also means, though, it can come out and move across mud. So they decided to kill this whole pond. Cyanide. Wiped out the entire, drained the pond, wiped out everything in it. I think it was a little more than 1,000 snakeheads of all sorts of ages. Problem was, then they started finding them in the canal, in the Potomac River. So they definitely escaped. And they're like, maybe it's just a few. Maybe it's okay. Turns out then they found pregnant females in there. And now the northern snakehead is eating up the Potomac, heading into the Chesapeake Bay.
Did some person get like sued?
Yeah, they totally did, but they were really sorry.
I believe it.
Yeah.
There has to be some sort of like,
There's consequence. Yeah, no.
you know?
There was a civil fee, but it's nothing compared to the damage that was caused. It's just like when somebody accidentally starts a wildfire in Florida. There's a fee, but it's not nearly enough to cover the damages.
I feel kind of bad for them because they were just uneducated, I think.
They were really, yeah. And they thought they were doing a good, they were trying to do good.
It's so sad.
Yes,
Why did they make a fish in the first place?
because it was for medicine. They wanted to make a special soup for their family with it.
I didn't know that. Okay. I thought it was just like a dinner that they
Yep.
No, the family member was sick, and then like they got better, so they didn't eat fish anymore. And then they crossed everything out.
Yeah. Two more examples of invasive species, and then I'll leave this topic alone. One is the cane frog.
The Yeti crab.
Oh, I don't even know what the Yeti crab is. We'll talk. The cane frog was introduced into Australia, and now it's everywhere in Australia to the point that there are literally people who enjoy days of just driving around the roads, running them over. They are everywhere, and they're out eating the local wildlife. Dingoes in Australia were invasive. Wild dogs. People went down to explore Australia. They brought their dog. The dog went loose. Mated with another dog that went loose, and now there are wild dogs everywhere. Top of the food chain predator. Cane frogs, dingoes. There's one more. Oh, there's this. Do you guys know what crayfish are? Okay. There is a crayfish in Germany right now that has adapted a way to clone itself. It does not need any other biological support. It's a female crayfish that will just clone itself over and over and over again. The eggs she lays grow up to become fully fledged genetic copies of that one crayfish. This is one that we created in a aquarium by accident, and somebody let it go. And now it's just eating its way through the streams of Germany.
This is like a bee thing all over it.
This is. We just don't learn.
Stop releasing or doing anything.
Yes.
That is dreaming fault too.
Was that an intern's fault? No, it was likely a hobby aquarium person. And they just emptied out their fish tank, and it happened to have eggs in it. Doesn't need a hobby. Forget the whole organismal thing, just watch Netflix. So there are lots of things going on there. Now we're going to move into slightly less interesting things. There are lots of things that limit distribution. We talked about some abiotic things. Here are some biotic things. If one species preys on another in the area, then that prey species is going to be prevented from dispersing to a larger area. If you're eaten, you can't go somewhere else. The more predators there are, the more check there is on that prey. Abiotic factors that might stop Dispersal would be like temperature, presence of water, the amount of oxygen present, salinity, sunlight. If it's too salty, you can't go there. Especially slugs. They can't get where it's too salty. If there's not enough oxygen in like water, organisms can't survive. If there's not enough oxygen at the top of a mountain, you can't survive. If you were to go and try and climb, I don't know, the Himalayas, you need to bring your own oxygen with you. Most other organisms don't have that ability. It's not like you can get, you see a deer strapping on an oxygen pack to go to a higher elevation to eat more. So both these biotic factors and these abiotic factors are going to influence density and dispersion. We haven't talked about density yet, right? So here's where we talk about density. Population density is the amount of organisms per unit area. In Chesterfield, we have a much higher population density than out in the countryside. There are more people living in one square unit of the area. Population density is always changing. This is a map of Virginia since 2010. And you'll notice there's some regions of the state where you got a declining population. Typically, the much more rural areas. There's some areas of the state that are increasing in population. Which one's us? Are we this one? This red one here? You guys don't know geography either? Yeah, it's by county. I think that might be Richmond, but I'm not sure. It's somewhere in here. Well, tell you what. You think we're that one?
The map is strong.
No, I don't think. No, that's definitely not. Okay, so apparently, I'm going to take a quick break.
It's so empty.
So the way that these population densities are going to increase is through immigration, where organisms are brought into an area, or birth. The higher the birth rate, the more likely you are to have an increased population. If your birth rate is greater than the rate of death, your population levels will grow. Populations shrink due to emigration, or leaving an area, or due to death. Death is a major factor here. That will limit the growth of populations. So you can have organisms coming in, you can have organisms leaving. Once the organisms are in a region, though, they're going to disperse themselves following certain characteristics. They can be either clumped or they can be uniform. Clumping is probably the most common dispersion pattern. This is where you get individuals aggregating in patches. This is where you get people living in neighborhoods. They tend to live together. We're social creatures. These elephants hanging out as a group. You hang out as a family. That's contrasted with territoriality, where you get a uniform dispersion, where organisms that are directly interacting or directly competing with each other are going to limit how close they can get. If you had multiple megalodon, they could not all live in the same area because they would need to hunt different organisms, the same very large organisms. These trees are evenly spaced. Coyote packs, or I'm sorry, not packs of coyotes. Let's go with like individual predators. A bear should not clump with another bear. Mountain lions, they're solitary. But that's, yeah, that was just for coolness. Plus, if they're fighting each other, though, they're fighting each other to establish territory. To figure out... Oh, well, that's different. So population growth can be described as either exponential or logistic. This is math, right? They can be increasing or they can be decreasing. Exponential growth is where you grow as if with exponents. You guys remember exponents, right? So what's like 2 to the 0 power? 1. What's 2 to the first power? 2 to the second power. 2 to the third power. 8. Yeah, okay, we're getting a little bit more iffy. 2 to the fourth power. 16. But you see, you're rising very, very quickly. That's exponential growth. It's logistic when you hit what's called the carrying capacity. When you hit a point where that growth cannot be sustained, it levels off. Feral cat colonies grow through exponential growth. Anybody feed cats outside? Good. Your neighbor's crazy. Are the cats spayed by chance? Do you know? No? Yeah. So what ends up happening with a feral cat colony is you start off with 2 cats. Those 2 cats may produce 4 cats per litter, 4 kittens per litter that survive. Does that 3 times a year, so 12 cats a year per female. And then the next year, you're rising even more, and even more, and even more. That's exponential growth. But the problem is, even with feral cat colonies, you reach a point where you run out of resources. You don't have the old lady dropping off a bunch of, I assume it's an older lady, dropping off all this food for the cats to eat. They run out, which means it reaches that carrying capacity. It reaches that level where there are not enough resources. Exponential growth will keep happening as long as food is present. What?
I don't know why I find it funny.
It's the fish. When you hit that point where the resources limit the growth, you've hit the carrying capacity. This puts a cap on the total number of organisms that can live in an area. This is going to get really, really scary for humans because the Earth has a certain carrying capacity. And we are still growing our population. If you think about a fish tank, how many, anybody have a fish tank by chance? No, because you watch Netflix. And you don't need a fish tank to have a hobby. It's just dirty. They get dirty because you got too many fish in there. There's a certain carrying capacity. Typically people say like 1 inch per gallon of fish. You can only have so much in there. I used to keep Daphnia magna, water fleas, for a Bio 102 class in an aquarium. And I thought it was a brilliant way of displaying this concept, because what would happen is we get the water fleas in, we'd probably get 20 or 30 of them, and they'd very quickly start consuming the resources. The food that was with them, they'd multiply out. Eventually we'd have like 2,000 or 3,000 swimming around in there. But they'd hit the carrying capacity. There's not enough oxygen in the tank to support that many organisms. The oxygen levels decline, and then the population drops. I didn't need a bigger tank. I used them for what I needed them for. And then I showed this concept, and it was really cool. So you've got these, as population growth reaches that carrying capacity, the rate of population growth reaches 0. So you start off with a certain number, that number increases, and then the growth levels off. Populations will reach this point where there's no population growth. So these population dynamics, this rising population, dropping population, are going to ultimately be influenced by sort of the population density and also the life history traits of this organism, whatever the organism may be. So what this graph is showing is population size compared to deer quality and ultimate deer production. So deer production is how many deer are being produced.
What do they mean quality?
Quality? Is the deer in bad shape? Is it a small deer? Does it not have enough food? And what you find is deer quality diminishes based on the population size. The more deer there are, the less resources there are for the whole population. So populations are sort of in this dynamic flux. You may have some very high-quality organisms and some very low-quality organisms based on the number of organisms of that population present. So some of the life history traits of these organisms are going to be like its life expectancy can be determined by the number of individuals surviving. For humans, we have a lot of individuals surviving and a very long life expectancy, because we invest a whole lot of resources in raising a human. That's compared to trees. Plants. Plants will produce a whole lot of organisms to begin with, but most of them don't survive to adulthood. Most of the trees that are starting to grow, we cut down with like a lawnmower. Little seedlings that are growing in the ground, what do? You rip them out. You don't let all trees grow. So there are three big variables that are going to sort of influence your life history. When reproduction begins, so what age do you reproduce? Some organisms can reproduce right away. Other organisms take a long time. How often that organism will reproduce, and how many offspring are produced per reproductive episode, or per time they get pregnant. Let's think about us, humans. About what age are we reproductively capable? Not when it's societally acceptable to reproduce. 12, 13, around there. Low end, 12, 13 years. Capable of reproduction. How many offspring do we have per episode? One, usually, normally. There's some odd occasions, but the normal is one. How often can we have offspring? Roughly, about once a year. Every 10 months. And then we could do that, well, yeah, technically, but it'll be easier for math for once a year. So, and then you could reproduce successfully, possibly, up until 36 to 38. And then you see a start decline. So you're looking at, what, about 25 years? One of us can produce 25 organisms over the course of their life. If that's maximizing everything. And that's, no, I'm just maximizing things. Because then the counterexample is, look at cats. How fast can cats reproduce? Every day. But they by about 2 years, right? Or a year? Is it a year? Yeah. So they're capable of reproduction after 1 year. They're capable of producing lots of offspring. What? Let's even just go sort of lower end, 4 or 5 per batch. Every year they can have 3 batches, so that's 20 a year for, how long does a cat live? 15 years? And this is really important to me because I want my cats to die. So 15 is what I'm kind of hoping.
Some can go higher.
No.
Longer than,
all right.
I've seen ones like at my old job that were like 24.
Oh. All right. Well, let's just
like the really old end.
Let's just go with say 15, and so they can reproduce for about 14 years successfully. Because after you get a certain age with cats, you can't. It's that reproduction system's kind of on its way out. So 14 times 20 is 280, right? So whereas we're able to, over the course of our lifetime, produce 20 offspring at like most, or 25 at most, churn them out every year, cats can produce 280 in their lifetime. Very, very different life history traits.
Let's say 50, because twins, right? That might happen.
Like 25 times in a row. But even then, cats still got us beat.
I know, but I just want to, it's not how to be a landslide.
But it's still a landslide. 280 to 50.
I could have 50 children that
You need a bus. What allow these organisms to survive and compete are selective pressures. This is a trade-off between the number of organisms you produce and the size or the success of those organisms. Here you got different rats. Some rats, if they've got a high investment of energy, are going to be able to produce more offspring. The more resources they get, the more offspring they can produce. Or the more resources they get, the bigger and more fit those offspring might be. Plants and animals whose young are more likely to die often produce many, many, many small offspring. Plants produce a whole bunch of seeds, and they hope they take. Tons of them. And if one survives, great. Small organisms, mice, produce tons of offspring. Heck, roaches, ants, tons and tons and tons of offspring. Those offspring are likely to die, but in the end, it's not going to affect the overall population. For other organisms like us, extra investment on the part of the parent increases the survival of the offspring. So if you take the time, instead of having another kid right away, to raise that one you've already got, that kid is likely to do well. You could go with sort of Riley's idea of having 50 kids, and hopefully one of them will survive. Or you have 1 or 2, and you invest a lot of resources into making sure they survive. Whenever you have high population densities, you also have competition. So if you're competing with a lot of other organisms in that region, by investing in your offspring, you're able to help that offspring survive that competitive world. Pretty sure most of you guys have parents. Actually, yeah, so because you didn't just spring out of nowhere, no matter what you may want to think. And your parents invested in you to help you compete with other people, with other offspring of other people. I assume, right? Your parents, did they, I don't know, help you with your homework occasionally? Yeah? No, you're like, my parents couldn't read. Your parents did what they could. Okay, so here's my parents. My family immigrated to the country. And neither of my parents had a college degree, but they were dead set that their kids were going to have that advantage. So they worked, and they adapted to the system, and they got my sisters and I to college. It was hard. They worked really, really hard. The resources they could have used to have another kid or 2 or 50 were completely wasted on me and my 2 sisters. Some of you guys are an only child, right? Or all of you, do all of you have siblings? You all have siblings? Okay, you've met that only child, haven't you? You know them, you've seen them, and they get like everything they want. Yeah, and you're like, why couldn't that be me? Harry Potter reference here. So, you guys know Harry Potter, I assume. My son was reading Harry Potter, and he had to answer the question, if you could be any character in the book, any character at all in the book, who would you be? What? He chose Dudley Dursley. Why did he choose Dudley Dursley? Because he got 37 presents. He got all the gifts. He got all the attention. He's like, I just want my parents to give me everything and my sister nothing. Now, for a 10-year-old to say that, I framed that one. But it's that idea. You have a single offspring. You can give them as many resources as you want. You have 2, you have to split the resources. You have 50, you're just not even giving them anything at that point. So by giving resources, you help them compete better. There are some situations where population density might be impacted by density-independent events. That is, events that will happen no matter what the density of the population is. Wildfires. What would happen in a wildfire to a population of trees? It burns down. What if there was a smaller population? It would still burn down. Tornadoes. These weather-based events are typically population-independent. The birth rate or the death rate does not get altered based on the level of the population. Afterwards, what do you think will happen? After these events, you've now cleared out an entire ecological niche. What? Adaptive radiation. You're going to have, or in the shorter term, you'll just have dispersal, or new organisms will come into the region and colonize it. This is compared to density-dependent variables. These are going to change the rate of birth or death, and it is totally dependent on the population, like how much prey is present. Show you a bunch of these. Lots of different ways of density-dependent regulation. Competition for resources, the amount of toxic byproducts created, predation, territoriality, and disease. There are only so many resources in an environment, and organisms must compete for them. When those resources run out, there's nothing else. Competition will limit the number of organisms available in an area based on the density of that population. Toxic waste products. You are constantly producing toxic waste products. You excrete a substantial amount. There are other organisms out there excreting a substantial amount. When the levels of those byproducts build up in a region, that region cannot sustain that level of life anymore. For instance, London. London in the 1500s. I'm talking about human excretion. There's only so many people that could live in London because they had to move all of the feces out. Now the issue is, there's no running water. Well, there kind of was when it rained. Water ran down the streets. So people would take whatever waste they created in the night and dump it into the street. That would then eventually get sent down to the Thames, the river, the source of drinking water. The more people that were there excreting, the less healthy it was, so the more people that were dying. It regulated the population. Predation. Predation always regulates the population. The more prey you have, the more resources there are for predators to survive and eat and reproduce. So the more predators you have, thus decreasing the amount of prey you have, and then regulating, in turn, the number of predators that can survive. Territoriality. Some people really like their own space. A lot of you guys probably have your own room. You don't want to share it, I assume. I might be mistaken. Maybe you want to share it. You're just very nice and open. But if you've got your own room, you understand what it's like to have a territory. Is your room too small? Or is it the right size? Most people say their room's too small. You want to expand? There's only so much space to expand. You guys, you just told me you all have siblings. You would sure love to take their room as like a closet or a game room or something else. Got to get rid of them for that. Lots of ways to do that. Not encouraging it. Help them go to college. Territoriality. You want a bigger territory, and so does everybody else. Disease. The larger the population, the more likely it is for disease to wipe out parts of that population. So as population levels go up, disease becomes a greater factor. As population density decreases, the less likely you are to spread that disease. Zombie outbreak happens. Where do you not want to be? The city. What? No, in the middle of it. You don't want to be outside. So you always see zombie outbreak movies start off in a city, right? And what happens? All of those people who are densely packed in there get infected, and then you have a whole zombie horde to deal with. Where do you end up surviving? The shopping mall. You don't survive there very long. That's Romero's big thing. Look at Walking Dead, season 2, they went out to the farm. They did well there because it's far away. It's density dependent. There's less people there, greater chance of survival. Diseases spread quickly in a high population. So, these populations are constantly shifting. Interactions between one organism and another, between that organism and its environment, are constantly going to be causing the levels of one population or another to increase or decline. These organisms are utterly dependent on each other. Changes in one population end up impacting changes in the other populations. As the amount of algae increases, the amount of toxic waste, this is what's happening in Florida right now. You guys have read about, there's sludge in all of the Florida canals. There's a red tide, I think, that's increasing in strength. This algae is producing a toxic waste product. That toxic waste product, it's not hurting the algae, but it's killing all the fish. And if all the fish are dying, all these other organisms are dying. So as the population level of the algae increases, you're correspondingly decreasing the population of these other species. Well, it would, except it's not all the way out into the reefs. It's just by shore. You know, where we go. So ecology is really a science of studying population growth and decreases, studying interactions between species and their environment. And that's what we're going to be covering for the rest of the semester. That was a really good conclusion, too. I'm proud of myself on getting to that one. Do you guys have any questions?